Hello. In this video, we'll introduce three new formulas which will help you to find the sum of arithmetic and geometric sequences, and in some cases, infinite sums. Let's get started. So to begin, we remind ourselves that an arithmetic sum was one in which each term is separated by a common difference. So let's examine our first example. 1 plus 2 plus 3, continuing like this, plus 100. How could we find the sum of those terms? Now, you could get your calculator out right now, like a friend of mine did once, and start adding 1 plus 2 plus 3 plus 4 until you get to 100. But that would take a lot of time. We're prone to error, and there must be a faster way. In fact, there is, because this pattern is called an arithmetic sequence, and we've studied those in our last video. In fact, if you'd like to pause this video and go back to the previous one, that might be a good idea in case you're not familiar again with what the arithmetic sequence looks like. Now, because it's an arithmetic sequence, we can see that there is a common difference. In this case, our common difference is what? That's right, it's 1. Each term is increasing by 1, so D is 1. And our first term, our A1, A sub 1, happens to also be 1. This is a very basic sequence. Now, on the right of your screen, you'll see a formula that says capital S subscript n. We read that as the sum of the first n terms. And the formula says take n, which is the term number that you go out to, times it by the first term a1 plus your nth term, the term you're stopping at, a sub n. Take that sum, multiply it by n, and then cut it in half. Now, why is that? What I'd like to do for a moment is walk you through this particular example and then show you how the formula makes sense. For example, if you were to take your first term 1, and combine it with your last term, your nth term in this case. Here your nth term, your last term, is 100. You would see that 1 plus 100 is 101. That's exactly right. But what about if you take 2 plus the number right before 100? What would the number right before 100 be if we're going up by 1 each time? That's right, it would be 99. So if you were to add 2 plus 99, what would you get? That's right, 101. So once again, we're getting 101. But what if we took 3 and we added it with the number right before 99? Well, that would be 98. And 3 plus 98 is, you guessed it, 101. So do you sense a pattern here? That's right. We're saying if you were to just take 1 plus 100, you get 101. And that's what we're being told to do in our formula here. We're taking 1, our first term, plus 100, our nth term. That gave us 101. But how many copies of 101 do we really have? Well, let's think about it. There were 100 terms, it looks like here, because we increased by 1 each time. So if there were 100 terms here, and we paired them up, how many pairs do we have? In other words, didn't we just divide by 2? Exactly. So if you divide it by 2, you really are saying, I have 50 copies of 101. Well, that's the same as what the formula tells you to do. To find the sum of the first 100 terms, so S sub 100, we really took our number of terms, which in this case was 100, we multiplied it by 101, and then we cut the whole thing in half. Or in other words, we took 50 and multiplied it by 101. Either way, we should be getting that the sum of the first 100 terms of this arithmetic sequence is, that's right, 5,050. All right. So that would be the total sum if you added 1 plus 2 plus 3 plus 4 until you got to 100. So anytime we see an arithmetic sequence like this where we have a common difference between terms and we like to add up the sum of the first n terms, the things that we need are how many terms are there, and sometimes that takes some thinking. What is our first term and what is our last term? Add those together and multiply by half of the number of terms. That's our formula. So this is another one of those formulas for this chapter on sequences that you'll want to commit to memory and practice, recognize when you can use it, when you can't. Let's take a look at our second type of special sum formula. And that is for the sum of the first n terms for a geometric sequence. Remember, geometric sequences in our last video were sequences which instead of a common difference increasing in a linear manner, we had a common ratio. So we're repeatedly multiplying each time by the same number. It ends up to be exponential, doesn't it? So let's take a look at this example and then we'll build our formula together. We have 2 plus 4 plus 8 plus 16 plus ... which means continue this way, plus 1,024. So we're asked to add up the terms of this geometric sequence. So again, you would have to recognize as you move into calculus and other future math classes, you have to recognize the pattern yourself. So you would say to yourself, self, what's going on between consecutive terms? Am I adding the same number each time, or am I multiplying by the same number each time? Or neither one, right? We don't always have arithmetic or geometric sequences. Well, that's right, we are multiplying by 2 each time. So we have a common ratio in this example, a common ratio of 2, because 4 divided by 2 is 2, 8 divided by 4 is 2, 16 divided by 8 is 2, etc. A common ratio. We also have our first term as the number 2. Okay? Well, instead of going through a laborious process of proving this, I would recommend that you look in the book for this formula. There is a step-by-step proof in the ebook or the regular hard copy. But for the sake of time, let's go ahead and take it on faith that this is in fact the pattern for the sum of the first n terms of this geometric sequence. What would we need to continue with the formula? Well, we would need the first term, which we now know is 2. We know this is our a sub 1 here, our first term. We need to multiply it by 1 minus r, where r was the common ratio, in this case, 2, to the nth power, we're going to talk about that in a moment, all over parentheses 1 minus r, so 1 minus 2 in our case. So the question here is, what is n? And this is where you have to do a little more thinking from our previous video about arithmetic and geometric sequences. If you remember that if you truly have a geometric sequence, what was your general term, the nth term a sub n? You started with your first term, and then did you add or multiply by r? That's right, you multiplied by how many copies of r? That's right, n minus 1 was your exponent. That's how many copies of r you multiplied by to get to that term. So if this was your generic term for a geometric sequence, and again, you can go back to your previous video if you need to, then what would the n be in this situation if we're stopping at the term which is 1024? So basically we want to know what term number is that. Well, we need to know what the pattern is for our general term here. So let's plug in chug. A sub 1 is 2. R was also 2 to the n minus 1. And that whole thing should equal 1024 for the nth term. So our nth term is known to be 1024. Right there. So with that in mind, what do? Well, a little bit of algebra would be helpful here. You could either divide both sides by 2 to isolate the exponential piece, or my preference would be to know my power rules for exponents, because if we have the same base, let me write that up here for you again, b times the same base b, but different exponents m and n. Do you remember how we combined those exponents? That's right, by addition. It was b to the m plus n. So whenever you can recognize a pattern from your previous algebra classes, that can save you time. And that's what's happening here if you want to save time, because 2 is really 2 to the 1. 2 to the 1 times 2 to the n minus 1 would be 2 to whatever the sum of those powers are. Well, what is 1 plus n minus 1? The 1's cancel. Isn't it just n? So I would have that 2 to the n equals 1024. Now, if you're having heart palpitations because this is reminding you of a previous chapter about exponential functions and logarithms, it's okay. You don't actually need to use logarithms here, because we learned when we studied exponential functions that as long as you can rewrite both sides of an equation with the same base, you simply know that the exponents must be equal. So can you think or use your calculator to determine 2 to what power, which would give you 1024? You can check, pause the video, feel free to try it on your own. That's right, it's when n is 10. So it looks like in this case, this is our 10th term, okay? So now we know what n is for the sum. We're saying we would like the sum of the first 10 terms of this sequence. So in our formula, we would have 2 times 1 minus r, which was 2, to the 10th power. That is our 10th term. And you can plug it in. Does that make sense? If you put 10 into your formula, do you in fact get 1024? That's how you would know if you have the right formula. All over 1 minus r, but 1 minus 2, which was r, is really negative 1. So now it's back to basic algebra. Can you follow order of operations correctly to get the correct outcome? So let's take a look at what we have to do first. Remember, order of operations says PEMDAS. Please excuse my dear Aunt Sally here in America. If you grew up overseas, maybe you know BIDMOS. They mean the same thing, okay? The idea is our grouping symbols first. Well, in our grouping symbols, we have some operations to do. What operations? We have to do our exponents before we multiply or divide. So we have to take care of 2 Notice that was a positive 2, it wasn't a negative 2. 2 to the 10th power. And we already know what that is. That was 1024. So we would have 2 copies of 1 minus 1024. Running out of space there, I'll erase in a moment for you. All over negative 1. So we have 2 times, parentheses, 1 minus 1024 all over negative 1. Well, 2 divided by a negative 1 is just negative 2. So this should really end up equaling negative 2 times negative 1023. So let's write that out. So negative 2 times negative 1023. So your final answer should be positive. In fact, the final answer is in fact 2046. Now, if you remember from our previous video, we talked about how you could use technology to check, typing in the summation symbols, the sum of the first n terms. So you could actually plug this in using your technology and verify that yes, the sum of the sequence starting at n equals 1, stopping at n equals 10 is in fact 2046. All right, so this is the hardest of the formulas in this chapter, I promise. On the next slide, we'll practice some more of these formulas as well as introduce an infinite sum. Let's take a look at our next slide. It says, example 1, find the partial, meaning not for infinity, but just the first however many terms. Find the partial sum below. 6 plus 2 plus 2 over 3 plus 2 over 9 plus ... Now, before I keep reading, I want to point out that if it stopped there, plus ... and that was the end of the statement, then that would be asking you to find an infinite sum that goes on forever. But notice after the semicolon, it says, find S sub 10. So again, they're asking you to find the sum of the first 10 terms only. So not forever, stop at 10. Well, we recognize what type of sequence this is. If you start with 6 and jump down to 2, and then you start from 2 and jump down to 2/3, and then from 2/3 you jump down to 2/9, what's really happening each time to our consecutive terms? Do we have a common difference or do we have a common ratio? That's right, we have a common ratio. What is it? Well, 2 over 6 is really reduced to 1 over 3. And if you divide 1 over 3, if you multiply 1 over 3 again by 2, don't you get 2/3? And if you multiply by 2/3 by 1/3 again, you'll get 2/9. So it does seem that we're repeatedly multiplying the previous term by 1/3 to get to the next term. So this is in fact a geometric situation, a geometric sequence, if you will. Again, feel free to go back to your previous video if you need to review that skill of recognizing which sequence you have. But now that you've recognized what type of sequence it is, your job is to answer the question. They would like us to find the sum of the first 10 terms. So this is pattern recognition. It's a geometric situation, and we have a sum, a partial sum, because it's just the sum of the first n terms, where n here is 10. We want to stop when n is 10. Only go up to the first 10 terms. So we could write this out. In fact, on my not take home, I never do that, but in my face-to-face classes, when they have show your work tests, I've seen students take the long way here, where they actually will write out every single term and then add them up the long way. Please don't be that student. Learn these tricks and save yourself time. And if you're going to calculus, you will have to know these patterns and recognize them. Okay, but yes, you technically could write them out and add them up. Okay, so now what do we do? Well, what we're going to do is remember our formula. And I don't suppose that you've memorized it yet, so you can go pause the video, go back to the previous slide and write it down if you haven't done so already. And at any point, feel free to pause and try it yourself. So what is that formula? It said we would take our first term a1 times 1 minus r to the nth power, but here n is 10, that's our term number, over 1 minus r. Now this time our r, that's kind of hard to say, our common ratio r, is in fact a number which is less than 1. That's going to be very meaningful to us in our final slide, in our final examples today, because it turns out that if your common ratio for a geometric sequence is less than 1, or I should say its absolute value is less than 1 to be specific, that over and over again as you get to your next term, they're getting smaller and smaller, aren't they? Because you repeatedly are dividing by numbers. And over again when you do that, you're getting a smaller and smaller number, so you're infinitesimally getting closer to 0, which means you can approach an actual number that we're going to call our convergence of our infinite series. Okay, so we will go to that extent for this example in a few moments. But for now, let's just find the sum of the first 10 terms, since that's what we've been tasked with. So we're going to plug and chug here. We know that our first term that was given to us was a 6 times 1 minus r, where r is 1/3. Here I'll use parentheses to remind myself that if I have a fraction raised to a power, I'm really multiplying both the numerator and the denominator, however many copies the exponent is. So I multiply both of them to that power, raise both to that power. So this is 1/3 to the 10th power. And then for my denominator, I have 1 minus r again. So 1 minus 1/3. Don't really need parentheses there because I'm not using an exponent. So what ends up happening? Well, you could do the denominator first. That's pretty obvious. 1 minus 1/3 is really 2/3, isn't it? If you want to use parentheses, feel more than welcome to. So I have 6 on top multiplied by something, and then I'm dividing by 2/3. But what am I multiplying by? And this is where your algebra skills have to really become strong if they're not there already, okay? So what are we doing? Well, we're taking 1/3 to the 10th power, which means 1 to the 10th power, but 1 times 1 times 1 10 times is just 1. What is 3 to the 10th power? You can check your calculator. I'm getting 59,049. So that is the result of 3 to the 10th power, 59,049. Then I'm supposed to take 1 minus that fraction. Now, here's a note of caution here. Here's a quick note of caution. When you're doing these problems, right at this step, a lot of students don't like fractions in America, and that's going to be something you're going to have to overcome if you go on in math. But one of the things that the students become too used to is just using their calculator at this step. And if you use your calculator right now, what will usually happen is it will have an overflow error, or it'll give you a decimal that you might round with, and that would make your answer not quite right. So what I would recommend is to recognize that anytime you have 1 minus 1 over something, like 1 minus 1 over 3, let's say, what did we really know? Well, that's really 3 over 3 minus 1 over 3, or 3 minus 1 over 3, so 2/3. Why did I use that easy example? So that you could see the pattern is the same. 1 minus 1 over something is really this denominator over itself, that's what we did right here, minus 1. So a shortcut is your numerator should just be 1 smaller than your denominator. So this should just end up being 6 copies of 59,048 after that subtraction over the denominator 59,049, all divided by 2/3. That's called a complex fraction from your previous algebra classes. You might not have liked them, but they're back. Okay, so at this point, I want to erase that example so it's not confusing later for you. At this point, this is where we're at. We have to keep simplifying, and again, your calculator will probably give you a rounded version, which is not quite right, or it will have an error, so don't use your calculator too soon. But here you could do a little bit more algebra simplification yourself, because you know that 6 divided by 2/3 is really keep, change, flip, or 6 times the reciprocal of 2/3, or 6 times 3/2. And then that result gets multiplied by your big fraction here, 59,048 over 59,049. So in the end, I know we're almost there, it's almost the end for this problem. We have 6 times 3, which is 18, divided by 2, which is 9. So I'm just going to write 9, if that's okay with any of you, I hope. So that's a 9. And then you have 2 choices right now. You can multiply 9 by 59,048, get a massive number. I think it's 531,432 over 59,049. But my preference, and hopefully yours too, is to always reduce when possible. So notice here that 9 goes into 59,049, a total of 6,561. So the final answer for this problem would just be your numerator of 59,048 over your new reduced denominator of 6,561. Okay, so I'm going to erase there and rewrite it up here so you can see it better. Now, what's interesting about that is if we got the decimal, let me show you what that would be really close to. If you take 59,048 divided by your reduced denominator of 6,561. It turns out, go ahead and do it now, go to your calculator and find out what that is approximately equal to, let's say to 4 decimal places. What'd you get? That's right, 8.998, if you will, right? So that's really, really close to 9, and that's just the sum of the first 10 terms of this geometric sequence. So if you were to guess right now that if you kept going out further and further for the terms of this sequence, what do you think the sum is going to approach? Any ideas? Maybe 9? Yeah, you could even check with your technology and see, am I getting closer and closer and closer to 9? And you actually are converging to 9. And in the next slide, we're going to show you why that is. It has to do with the fact that as you take your r, which is less than 1, and raise it to higher and higher powers, it gets smaller and smaller and smaller, closer and closer to 0, meaning your formula becomes a lot cleaner. Let's take a look at our last slide, or second to last slide, which will show this last formula. This is called the convergent geometric series, and it again only applies in one special case. If you have a common ratio whose absolute value is less than 1. So it could be r equals negative 1/3 or r equals positive 1/3. Both cases would converge to a single number as your n values, as your terms get bigger and bigger. So one way of writing that, the tackier way, is s with a subscript of infinity, meaning we have an infinite sum. Another way of writing that is with limit notation, which is what you'll more commonly use in calculus. The limit with n approaching infinity on the bottom of your sum, s sub n, would equal the limit as n goes to infinity of your formula. So this was our formula from the previous slide for any geometric sequence. Now notice what happens as your r value is less than 1 and it's being raised to a number that is bigger and bigger and bigger and bigger, so as n gets larger and larger, that entire part would get closer and closer to 0. So you would end up with, the limit of that would be a sub 1 times 1 minus 0 over 1 minus r. As n gets really, really big, that fraction gets smaller and smaller. It approaches 0. Well, what is 1 minus 0? It's 1. And 1 times anything is itself. And that brings us to the easiest formula in the whole chapter. This is the formula that you'll use again and again whenever you have a geometric sequence that you're adding the terms of, but you're allowing the terms to go on forever. In other words, the infinite series for a geometric situation. So let's take a look at the previous example now. But notice this time, it doesn't tell you to stop at the first 10 terms. It says plus dot, dot, dot. So it's an infinite sum. This is an infinite sum for the geometric case where r is less than 1. So according to the formula, we would take our first term, which is 6, divided by 1 minus r, which we already found r to be 1/3 in the previous example. So 1 minus 1/3. And what would that mean? Well, that's 6 divided by 2/3. We did that earlier, didn't we? That was 6 times 3 over 2, or 18 cut in half, which is 9. What is this saying? Okay, you might be thinking, Professor, how can you go on forever? The idea is, as you keep getting bigger and bigger, that's what we mean by a limit. As you let n get closer and closer to infinity, as it grows larger and larger, your additional sequence terms are pretty much approaching 0. They're pretty much meaningless. So that's why your sum converges to 9, meaning that's like your limit, almost like a horizontal asymptote. You're getting closer and closer and closer to 9. In fact, if you put this in your calculator, find the sum of the first 100 terms, 1,000 terms, 1,000,000 terms. It'll say 8.999999999, as close as it can get to saying 9 without saying 9 precisely. Okay, well, let's see if you can recognize one of these patterns in our last example today. Example 2, find the infinite sum. We use summation notation in this example. I'll rewrite it in the appropriate way. It's kind of ugly here. Capital Greek letter sigma. On the bottom it says I equals 1. That means that's where we start. And on the top it says infinity. So that's where we stop. In other words, this is an infinite sum. What is the sequence? Well, it's 2 copies of parentheses 3 over 5 to the I minus 1. Now you might recognize right away that this is a geometric sequence. And if you do, feel free to pause the video and try it on your own with the appropriate formula. Okay, but how, if you're wondering, how does she recognize that? A couple ways. One is pattern recognition. For a geometric sequence, the pattern was my first term times my common ratio r raised to the n minus 1. And this one is just begging to be recognized, isn't it? Here we have a situation where our nth term is right here, right after the sigma, and it's standing for 2 copies of 3/5. In this case, they used I minus 1, so this is like your ith term, and then they're telling you where to start and where to stop. Start when I is 1, stop when I is infinity. Okay, so this is the sum of an infinite geometric sequence. But what is r here? R is 3/5. It's the base that's being raised to the power. Now here's one thing I want to caution you about. The reason I could simply use pattern recognition was because I started at 1. If I had started at 0, you would need to plug in 0 and find out what your first term really is in order to use this formula. So the first term may not have been 2 if I was 0. Okay, so watch out there. In this case, your first term is in fact 2, and you can check that out because if you plug in 1 minus 1 is 0, anything to the 0 power is 1, and 1 times 2 is 2. So 2 would be your first term because I is 1. So be careful there. Now let's plug in our formula. We know that the sum for an infinite geometric series, when r is less than 1, which it is a sub 1 over 1 minus r. Well, if a sub 1 is our first term, that must be 2 in this case. And if r is 3/5, then we'd have 1 minus 3/5 in the denominator. In other words, we have 2 over 1 minus 3/5, that's 2/5, that's right. In other words, we have 2 times the reciprocal of the denominator, which is 5 over 2. The 2's can cancel, and now we know that as you go on and on, adding the terms of this type of geometric sequence, because r was less than 1, the sum would converge to a single number. It gets closer and closer and closer to what number? 5. All right, so we've introduced 3 formulas today that work for arithmetic and geometric sequences for any n terms, but if we have an infinite sum, it'll be only the case where r is less than 1. So at this point, it's up to you. Go practice, because as always, math is not a spectator sport. I'll see you next time.